If you've watched a few of my channel's videos before, then you've likely noticed that every time a microcontroller comes up, I almost always pick an AVR. And while AVRs are a good choice for a lot of projects, it's sometimes a good idea to branch out every now and then and learn about new microcontrollers. And what better microcontroller to learn about than AVR's old rival, PIC. And as I've discovered, PICs are actually very capable and very interesting series of chips. So hopefully in this video I'll be able to teach you how PICs work, and eventually you can program your own PICs for your own projects. So without further ado, let's dive in. When getting started with any microcontroller project, you need three things. First, and most obviously, you need the actual microcontroller itself. Next, you will need a device to upload the code that you will write to the microcontroller. For these PIC devices, the official programmer is called the PIC kit. Now, there are several versions of this programmer, and they are differentiated by number. You get to choose between the PIC kit 2, PIC kit 3, and even the PIC kit 4 and 5. Now, which one should you choose? Well, I'll tell you the answer to that later in this video. For now, we have to talk about the third thing that you need, the actual software that you will use to write, compile, and upload your code to the microcontroller. But more on all of this in a second. Now, when selecting a microcontroller for your project, it's important to be as open-minded as possible. But for the sake of this video, we will narrow down our focus to just 8-bit PIC microcontrollers. You'll need to pick a microcontroller that has all the peripherals that you'll need. The PIC microcontrollers generally have a good selection of parts and peripherals to choose from. As for my microcontroller of choice, I went with the PIC 18F2450. It has the usual peripherals, like 3 timers, a USART, and an ADC. The standout peripheral on this MCU, though, is its USB capabilities. So it's definitely an interesting microcontroller, and it will make for a good test subject for this video. Before we can start writing code, we have to set up the bare minimum in terms of circuitry. This means that we have to supply power and any clock sources as needed. Luckily, there isn't much that goes into all this. It's simply just 5 volts to VDD and ground to VSS. You should also attach a 10K pull-up resistor to M-clear. This will keep it high normally, but it will allow our PIC kit to pull this pin low as needed. On the OSC1 and OSC2 pins, you should attach your crystal oscillator along with those 2 capacitors, if you decide to use one. You can alternatively leave it out if you want to use the internal oscillator instead. And finally, we have the programming header. If we take a look at the PIC kit pinout, we'll find the pins that correspond to M-clear, VDD, VSS, PGD, and PGC. It's pretty easy to connect everything, since they match up with the pin names. Beyond this point, everything is optional. So I went ahead and added an LED to RA0, which we will use to verify a blink program later on. Now we just need a way to communicate with our PIC from our computer. I showed you the PIC kit in the previous circuit example, and like I said earlier, the PIC kits are a good choice for this purpose. The PIC kit 2 and the PIC kit 3 have both been discontinued. However, they have been cloned to death. I myself am making this whole video using a PIC kit 3 which is cloned, so it can be a good option. However, like I said, they have been discontinued in favor of the newer PIC kits. This means that they do not support the newest chips. So I recommend that you check whether or not your specific PIC microcontroller will work with your PIC kit. I'd also like to briefly mention alternatives to the PIC kit, namely Microchip's ICD programmer. This programmer is more expensive than the PIC kit, but it should also be more reliable and professional. I don't have any experience with it though. You could also use one of the many DIY solutions that you will find on the internet, though these can be very frustrating to implement and they could take a lot of time to debug if something goes wrong. They are much cheaper though. So basically, the more you spend, the easier it will be to get everything working. There are a lot of different ways to write code for a microcontroller and then subsequently send that data over to the programmer. If you are inexperienced, you will want to pick up the MPLAB method for the most out-of-the-box experience, since Microchip has made it really difficult for other applications to be used. Anyways, let me show you how to install everything. First, go to the MPLAB-X webpage. I'll link it down in the description for easy access. It has a very straightforward installation process. Simply download the installer and run it and let it go through the prompts. Don't forget to allow the installer to add mplab to your path. Near the end of the process, you'll be prompted for a license key. To use the free version, just leave it as it is. We aren't done with the installation yet though. You will also have to install a compiler. Currently, Microchip recommends the XCA compiler. You can install it in a similar fashion as we did with mplab. I have linked it in the description. At this point, you should have the basic required software to get everything working. Now you can open mplab and click File, New Project. You'll be greeted with several different options, but for now just select Standalone Project. On the next screen, find your microcontroller underneath the Device section. My microcontroller is the PIC 18F2450, so that's what I chose. On the next screen, select the XCA compiler, which is what you just installed. And finally, name your project and save it wherever you'd like. Now that you've created your project, we will create the first file. First, click on Source Files. Then go to File, New File. Go to the C category and click C Main File. Change the file name to main.c and you are now ready to write some code. Our first program together will be Blink, so I'll walk you through the process. Go to your microcontroller's datasheet and find the I/O ports section. This section has all that you need to know about controlling the I/O ports. If you've watched my previous videos about AVR programming, then you'll notice that the I/O interface here is very similar to that found in AVR. The parallel to the data direction register in AVRs is the TRIS register here in PIC. This TRIS register will allow us to decide whether a certain pin is either an input or an output. What we will have to do is set the corresponding bit to a 0 to allow the pin to be an output. We want the LED on RA0 to be an output, so we will be dealing with the TRIS A register. To set RA0 as an output, you can simply write to the TRIS A0 bit directly. Now it's time to toggle the LED in the infinite loop. The register that we will use for this is the LAT register. It works in a similar way to the port register on AVRs. We can toggle our LED using the exclusive OR bitwise operator. And for our delay between blinks, I simply used a very long for loop to waste a bunch of CPU cycles. Now there is just one more thing that we need to do. We need to configure our config registers. The config bits are similar to the fuses on AVRs, and you can find the whole list of them on the datasheet in your Special Features of the CPU section. Now, there are a lot of settings, and luckily, mplab provides a tool that will set them for us. Go to Window, Target Memory Views, Configuration Bits. You'll see a whole window pop up at the bottom of your screen. You can go through and select which bits you'd like to enable. I changed mine so that PIC operates from the crystal. Once you're satisfied with your settings, click on the big Generate Source Code to Output button. This will compile your list, and it will open another window that will contain all of your bit settings. Simply copy everything in here and paste it into your main.c file. We are now ready to upload our code to the microcontroller. Go to the top of the screen and click on the button with a picture of the microcontroller and the green arrow pointing down. From here, click on Make and Program Device. You will be prompted as to which tool you will use. Make sure your PIC-Kit 3 is plugged in, because now you will select your programmer. Here, I'm using the PIC-Kit 3, so that's what I chose. After this, you can see everything working at the bottom. Any errors that you'll have will be reported here. And if everything goes properly, you should see Programming Verify Complete, and your LED will be blinking in real life. Now, I know that this video makes this whole process seem straightforward so far. And if mplab is cooperative with you, then it should be easy. However, mplab is also weirdly intermittent. I've had several occurrences where the connection to the programmer suddenly stopped working, and the fix to that was to simply restart mplab, which was rather annoying. Now that we have Blink completed, we can focus our attention on getting some of these peripherals working. Let's start with our timers. If we go to timer 0 on the datasheet, we will find that it is a very basic timer, which we can use as either an 8-bit or a 16-bit timer. You can also use it as a counter. It also has an overflow interrupt. So let's implement Blink again, but this time we will use the timer as our delay. I placed this green LED on RA1. which will act as our timer blink. To get started, we should take a look at the T0 con register, since this will allow us to get some timer settings. You can set up the prescaler, determine the clock source, and, most notably, decide whether it will be an 8-bit or 16-bit timer. For this example, I went with a 16-bit timer with an 8 times prescaler. The clock source is also the main system clock. Next, we will need to enable this timer's interrupt settings. The TMR0IE bit is located in the int con register, and it simply enables our overflow interrupt. The next bit, TMR0IP, is located in the int con2 register. This signifies whether or not the timer 0 interrupt is of a high or low priority interrupt. And to fully explain what that means, we will have to take a break to explain how interrupts work in this PIC. Basically, when defining your own interrupts, you can choose whether or not an interrupt is of a high or a low priority. Let's imagine an example scenario. Let's say that you've defined 2 interrupts. The first is a timer overflow, and you've assigned it a low priority. The other is a button press from the user, and you define this a high priority. Now let's say that the timer overflows and interrupts as usual. Then it starts processing its interrupt. Then the user suddenly presses the button in the middle of processing. Since the button press interrupt is of a higher priority, the low priority interrupt gets interrupted by the high priority interrupt. So as you can see, you can select certain interrupts to be more important than others. It's worth noting, however, that this interrupt priority system isn't present on all PICs. The PIC 18F2450 in particular has both this priority system and also has backward compatibility with the single priority interrupt system on the other PICs. For this video though, I will stick with the priority system since I think it really is a fascinating feature of this PIC. So, back to the actual project. To enable the priority system of interrupts, we have to set the IPEN bit. Afterwards, set the GIEH and the GIEL bits to enable both high priority and low priority interrupts respectively. And finally, to catch these interrupts, make 2 methods like shown for both high and low priority. Whether you decide to set the timer as high or low priority is up to you. But for whichever one you choose, place an if statement checking for the timer 0 overflow bit inside. Inside of this, we can now toggle our new green LED. Just don't forget to clear the flag at the end, or else you will be stuck in an infinite interrupt loop. Now there is just one more thing that we need to add to make everything work. Set TMR0 on to a 1 to enable our timer. And now we can admire our work after uploading the code. As you can see, that red LED is still running the original software blink program, and the green LED is running our new timer-based interrupt system, and it's blinking at a different rate than the red LED. The best part about all of this is that the green LED's code is nowhere to be found in the main loop. We can't just keep talking about timers without at least touching on PWM. Unfortunately, timer 0 does not have hardware PWM functionality, and you would need some sort of software intervention. However, timer 2 in conjunction with the CCP does allow for hardware PWM though. The timer 2 peripheral is rather simple in and of itself, with it simply being an 8-bit counter with a prescaler and a postscaler. It also has the PR2 register, which will define the top of the timer and will clear the CCP1 bit on reset. Now this is only half of the PWM problem. We still need a way to set the CCP1 output bit determined by a specific duty cycle. This is where that CCP peripheral comes in. It can perform a few different tasks, but we will set it into PWM mode by setting the CCP1M3 and CCP1M2 bits both to 1. At this point, we can set our duty cycle using the CCPR1L register and the DCB1 and the DCB0 bits. Yes, that's right. Our 10 bits are spread over that 8-bit register, and then those 2 other bits located in the CCP1 con register. To make setting all 10 duty cycle bits easier, I made a helper method that will divide the first 10 bits of this 16-bit integer up between the registers. Anyways, the CCP1 pin is located in the same spot as RC2. So we can modify trisc2 to be an output. And finally, we can simply turn on the timer using TMR2 on. The datasheet provides a setup guide for the whole PWM process as well if you're curious. Either way, we can't see much from here, other than the LED being on, of course. Let's open up the oscilloscope. Here we can see our PWM square wave operating at 5.8 kHz. The duty cycle here is 50%, because that's what I set it to in the code. If we instead change it to 25%, we will see much more off time while maintaining that same frequency. The actual LED is also much dimmer than before. If we go ahead and use a 75% duty cycle, we will see the opposite effect, and the LED will be much brighter. And all of this happens without using processing in the main loop. Here's a fun little bit of code that I wrote that will give a cool looking effect on the LED. Let me show you. Let's first enable the overflow interrupt on timer 2. You can do this in a similar manner to timer 0. I also set the post scale on timer 2 to 16 times with the T2 out PS bits. The main purpose of the post scaler is to essentially trigger the overflow interrupt once every 16 overflows on timer 2. Now inside of our interrupt code, we can dynamically adjust our duty cycle. To make this process easier, I made a structure that will hold data about our PWM settings. It stores the maximum duty cycle value that we'd like, the current duty cycle, which I called brightness, and finally direction. The reason why I included direction is because we are going to adjust the duty cycle both up and down. So inside of our interrupt, we will first check whether or not we are close to the minimum or maximum duty cycles. And if we are, we will switch directions if necessary. Afterwards, we will increment or decrement depending on the direction variable. And here's the result. We get this really nice looking breathing effect, with the LED smoothly alternating between dimming and brightening. We still have those two other blinking LEDs running at the same time too. There are a few other peripherals that I haven't talked about yet, like timer 1, the EU SART, and the 10-bit ADC, all of which should be somewhat self-explanatory depending on your skill level. In case you're curious, I'll still cover them briefly right now. Timer 1 is like the other two timers, but it also allows other functionality, like acting as a real-time clock or operating in capture mode using the CCP. The ADC simply takes an analog voltage on one of the analog pins and then converts it into a digital value. The EU SART is a serial communication peripheral, which may be useful for talking to your PC with over the serial port, for example. Your specific PIC microcontroller may have even other peripherals which mine doesn't. But I believe that the examples in this video should have equipped you to understand how to manipulate the registers and bits properly to get everything working. Now for the elephant in the room, the USB peripheral. It's honestly the star of this microcontroller, but I won't be covering it in this video, since it'd easily add another 20 minutes of runtime. And I'd like to keep this video about the basics of PICs. Don't worry though, I do plan on using this microcontroller in a future video in a proper project, so stay tuned for that. Well, it's time to sum up my experience with PIC and determine whether they can be used viably in projects. And my answer is a definite yes, so long as you are okay with Microchip's MPLAB software. Let's start by talking about the hardware itself. And I'd honestly say that the hardware and the supporting datasheet really are PIC's selling point. You can select from a wide range of microcontrollers with so many different combinations of peripherals. The other features are great too. For example, I really like that priority interrupt system, which isn't something that I've seen from my time with the Atmega series of AVRs. The datasheet that accompanies this microcontroller was also easy to read and follow. Now let's talk about the programmer. Like I've said and shown in this video, I have been using the PIC-Kit 3 programmer, or rather a clone of the original PIC-Kit 3. When this thing worked, it worked without a hitch. It was basically plug and play. However, there were a few times where it suddenly stopped working, and I'm not sure whether it was the PIC-Kit 3, the fact that this one is a clone, or that MPLAB was causing the issue. This was always an easy fix though, since all I had to do was restart MPLAB. I didn't really show much of it in the video, but the PIC-Kit 3 also worked great as a debugger, and it really helped me get timer 0 started. As for the software, if the hardware was the selling point of the PICs, then the software really is the main drawback. If you want to program PIC microcontrollers, then your best bet really is just to use MPLAB and the free version of XE8. You see, the problem here is that there really aren't any good free and open source tools out there for PICs. There is a project called SDCC, Small Device C Compiler, but PIC support is now unmaintained. If you do try to use it, it won't allow you to use the extended instruction set, and you are consistently warned to use the use non-free argument. The XC8 compiler, on the other hand, will lock you out of some compiler optimizations unless you buy the Pro license. I haven't purchased it though, so I can't tell you how well it works. So, in summary, if you're willing to put up with the MPLab environment, then PICs are a good candidate for microcontroller projects. Just don't forget to consider other options that may possibly have more longevity. Either way, I really want to thank you for watching the video up to this point. If you've enjoyed, please consider subscribing so that you can see my future videos. Also, check out my Buy Me a Coffee page, because with your support, I can keep making these videos. On that note, I would just like to thank Mr. Dev Null and Cognizant for being longtime channel members. You both have really made all of these videos possible, especially this one. Anyways, thanks for watching. Have a good one!